Hello, everybody, and welcome to the April edition of our SEAOSD lunch webinar. This month, we are co-presenting with the EERI San Diego chapter. Before we get into our presentation, I have a few chapter announcements. The first thing I would like to discuss is we have our Excellence in Structural Engineering Awards program coming up, and so applications for entries are now open. So please submit your presentation, your projects. We are very interested to see what you all been doing the last year, and we want to reward you for your success. Secondly, we have our SEAOSD golf tournament this year. It's at we're back to playing after a one-year hiatus. We'll be playing May 10th at a Twin Oaks Golf Course up in San Marcos. So we'd love to see you all out there. There are still plenty of sponsorships available, as well as opportunities to play. So I hope to see the entire membership out there on the golf course having a good time. Next, our next meeting is on May 18th. We'll be having basically part 2 of our presentation on the new SoFi Stadium up in Los Angeles. This presentation, we did a presentation in December where we had a joint meeting with ASCE where we talked a lot about the site logistics of the site, and this presentation will be focused more on the actual structural intricacies of the project. So I'm really excited to have Rafael Sabelli back with his team to talk about the structural systems of that building. We also, before we get to the EERI announcements, we also are in the midst of our call for nominations for our SEAOSD board. So if you're interested in participating on the board, we have a spot in our leadership track for vice president, as well as 2 board of directors spots available. So if you're interested, please contact anybody on the board, and we will put your name on the ballot. So with that, I will kick it over to Alvaro to do EERI chapter announcements.
Thanks, Steve. And thanks, everyone, for joining today. Thanks, Roy and Michael, for participating, donating your time today. And I just wanted to give you a quick update on the next EERI event. It's the 3rd Kenji Ishihara Colloquium Series on Earthquake Engineering. This year, the focus is going to be base isolation, damping systems, and soil structure interaction. Usually it's an in-person event. We usually do it at SDSU, but last year we skipped it, and this year is going to be 3 webinars of an hour and a half each, an hour and 45 minutes each, on 3 Fridays, starting on May 14. So if you're interested, please look at our website, SanDiegoEERI.org, and if you go to the next slide, that's the registration webpage that you're going to see. The dates are May 14, May 21st, and May 28th. Base isolation, damping systems, and soil structure interaction. Thank you.
Thank you, Alvaro. I am pleased to announce that this month we have a sponsor for our presentation this week. Or this month, sorry. We have a Sensaquake who will be doing a small presentation regarding their services and what they do. So I'd like to introduce Farshad. Unfortunately, I do not have your last name in front of you, but Farshad serves as the CEO of Sensaquake, winner of the Best Company Award for 2017 in Montreal, and has a PhD in structural engineering from McGill University. With the goal of bringing academic science into commercialization to make cities safer and smarter, Farshad has founded Sensaquake in 2015. Sensaquake is the first sensing-based platform for structural analysis and develops software, vibration sensors, and provides professional services based on its proprietary technologies. Instead of visual inspection, Sensaquake predictions are based on actual data from sensors deployed on structures. SenseQuake technology has been used to assess many landmark buildings and bridges across Canada, the United States, and Mexico, such as Canada's Parliament Building and the 2-mile new Champlain Bridge and the historic California Golf Club. Farshad is the recipient of the 2015-2016 William and Ray Seith Award, the highest distinction award from McGill University for the best invention of the year, and the Claudine and Stephen Brotman Award for the top 25 emerging entrepreneurs in Quebec. So take it away, Farshad.
Thanks for the nice introduction, and it's a great pleasure to sponsor the Structural Engineer Association of San Diego. Today, I will provide an overview of the new sensing-based technologies and applications for structural engineering. Just to confirm, can you see my screen?
Yes.
Okay, perfect. So when we think about instrumentation for structures, we normally think about having few permanent sensors on a structure, maybe get some alarms if there is an event. However, when we talk to asset owners in North America and structural engineers, majority of them were unhappy with the current systems on the market. There were enormous amount of information being measured, but not much use of data. That's the reason that we founded SenseQuake in 2015. We are a data analysis company that also manufacture our own vibration sensors. We use them as a tool to gather the data, which we follow up with our in-depth data analysis to come up with and extract different features for structural engineers and asset owners. We have 3 main technology streams. The first one is large system. It's a temporary sensing system. It's wireless. You can measure hundreds of locations in a structure just in a matter of few hours. And then we use our different software packages and in-depth data analysis for a few days or few weeks to extract different information from the data. We have our shake log permanent structural health monitoring system. It's a cable system. It has an IoT system. The main differentiation with other competitors such as Kinemetrics that you know in California is the amount of data analysis that we provide on top of whatever other information you get from those platforms. We also have Shake Zone, which is a 24/7 web-based dashboard to monitor vibrations at construction zones. The first system, the LARSA system, the temporary sensing test, very easy to use, measure hundreds of locations in the operational condition of the structure, follow up with in-depth data analysis and comprehensive reports. There are many different applications. I'm just showing here 3 of the applications we have with our temporary sensing system. The first one, getting all the baseline of the structure, resonance frequencies, mode shapes, and damping ratios. With the correct type of analysis, you can remove the environmental impact from these parameters to be able to perform periodic monitoring of the structures. You can detect the damage. You can also localize the damage based on these dynamic characteristics of the structure. For the first time, we have algorithms that are patented that we can use this one-time testing to predict the seismic performance of the structure. It is aligned with FEMA P58 fragility curves. Why people choose SenseQuake? We increase reliability, we detect hidden defects and damage points, we reduce the retrofit costs, it's non-destructive testing, we don't need any structural drawing. Our technologies have been used on landmark structures in Canada, US, and Mexico. And now I want to talk about our shake log. It's a permanent structural health monitoring system, and it's a 24/7 real-time monitoring system. It detects earthquakes, but it also provides in-depth data analysis. We always tell asset owners, if you want to have a state-of-the-art permanent system, you need a detailed baselining with a temporary sensing system, measure hundreds of locations that can be used for in-depth data analysis. Then we can identify the best locations that you can decide to put few permanent sensors in a structure. The 2 systems are complementary, and that will lead to the state-of-the-art health monitoring system. Our permanent system is capable of continuous monitoring of dynamic characteristics of the structure. We can detect damage based on our hybrid system, combination of our periodic monitoring system, detailed baselining, as well as our permanent dashboards. Few images of our web-based dashboards. You can monitor all these frequencies, mode shapes continuously with our dashboard. And then we capture seismic events. We can send alarms to the owners, to the engineers, and so on. Also, what differentiates SenseQuake platform is the fact that we can perform in-depth seismic evaluation of structures just based on the sensing tests with our patented algorithms. No need for visual inspections. If you have a new construction, you can also test the construction during this phase, compare construction with the design and the concepts and see if there is a change or there is any differentiation points before the building is fully outfitted. You can adjust your design and construction. In summary, we don't use any finite element model. We don't use any drawings. We are capable of capturing baseline of the structure, very important information to detect damage. We can continuously monitor model properties. For the first time, it's possible to perform seismic evaluation just based on this simple temporary testing or our permanent web-based dashboard. Many structural engineering firms in North America are using SenseQuake technologies. We also offer services to asset owners and engineers in North America. We have a very interesting partnership model for local engineering firms that are not familiar with these technologies, but they are looking to expand their service offerings in their local markets. If you're interested, please let us know. We can discuss the details afterwards. Thank you.
Thank you, Farshad. Thank you for a presentation. Your guys' company seems pretty amazing. What you guys are able to do with just some sensing equipment on there. So I'm very interested in seeing what you guys are capable of doing. So with that, I'm going to introduce our speakers in our presentation today. Our presentation is about the seismic instrumentation programs that both OSHPD and the City of San Diego are doing in response to recent code changes. So our first presenter today is Dr. Roy Lobo, who's a principal structural engineer with OSHPD, and he's been with OSHPD for over 17 years. Dr. Lobo received his doctoral degree in structural engineering from the University of Buffalo in New York in 1994. And prior to working at OSHPD, he worked with several reputed firms in the LA area. He's an active member of the structural engineering community with memberships in Structural Engineers Association of Central California and the American Society of Civil Engineers. He was the chair of the SEAOSD Seismology and Existing Building Committees and chair of the same committees for Central California, and he's currently a member of the SEAOSD Board of Directors. He's a voting member of ASCE 722 and ASCE 4123 committees and the chair of the ASCE 4123 Foundation Subcommittee. His expertise is in the field of nonlinear analysis and is the prime author of a computer program, IDARC 3D. In addition to his analytical background in computer modeling and software development, he's also has a vast design experience in the evaluation of retrofitting existing buildings. He's currently in charge of the OSHPD Structural Services Unit, and he's responsible for promulgating all necessary structural amendments to the California Building Standards Code to align with the mandates of the California Seismic Safety Act for hospital facilities. Our second speaker today is Michael Hill, who's a senior structural engineer with the City of San Diego Development Service Department, and he's been with the city for 7 years. He earned his bachelor's from Cal Poly SLO and master's from Cal Poly Pomona, and he's since worked for several firms in Los Angeles and San Diego area before joining the City of San Diego. He's an active member in the structural engineering community with memberships in the American Society of Civil Engineers, and he's a voting member of ASCE 722 Wind and Main committees and served on the California Code Advisory Committee. So with that, I would like to have Roy start speaking. So thank you, Roy.
Thank you, Steve. Appreciate everyone sitting in and listening to my presentation on seismic instrumentation program for OSHPD. You just saw a presentation on SenseQuake, so let me get into what our seismic instrumentation program is all about.
Roy, before you get started, I just wanted to announce to the people listening in at home that if you have any questions, please type them into the chat box. I will be monitoring it, and I will be relaying the questions to the speakers at the ends of their segments. So thank you.
Okay. Thank you, Steve. So why do we have a seismic instrumentation program? This seismic instrumentation program was started because of the damage from the San Fernando earthquake. So as you can see here, the devastation caused to hospital buildings was significant. Everybody knows the Olivia Hospital, the Veterans Hospital, you know, as you can see here, the stair tower collapsed. So this was what sparked the bad performance of hospital buildings and other buildings, sparked the initiation of the California Strong Motion Instrumentation Program and that was enacted into law in 1971. It created the strong motion instrumentation program such that Seismic will then install equipments and maintain these equipments in representative geological environments throughout the strait for different types of structures. So giving the code section there, you can look it up, and that's the San Fernando earthquake was the initiation of the strong motion instrumentation program. So if whatever program you have, somebody has to pay for it. So who is paying for this seismic instrumentation program is basically that's coming out of our permit fees. So depending on the cost of your building, your permit, per $100,000, there is a flat fee. There's a flat fee that goes towards payment of this seismic instrumentation program. So for residential buildings, it's one price. For different other buildings, it's a higher price. However, some buildings are not covered by these permit fees, and there's some exemptions to that. So the strong motion instrumentation program will not instrument certain types of buildings unless there is matching funds to instrument those types of buildings. And as you can see here, there are some exceptions, and hospitals, dams, bridges, etc. Some of them schools. So since I work for OSHPD, which is the building department for hospitals, that's what I'm going to be talking about today, and our instrumentation program. So as you can see, the seismic vulnerability of hospitals is well known. I showed you the earlier slide, and this is what led the legislator to respond to the failure of new buildings that did not perform well. And this was in 1971. So as you know, the 1973 codes changed to add seismic detailing aspects for buildings such that they can sustain strong motions like we experienced in the 1971 Silmar earthquake. So that was the response of the legislator, and created the Seismic Safety Act of 1983, which then made sure that new buildings are now under the jurisdiction of OSHPD. So it's that construction of new hospital buildings placed under state jurisdiction at FDD. So FDD stands for Facilities Development Division. And in 1991, Assembly Bill 41 put all aspects of building construction, hospital building construction, under FDD's jurisdiction. So what is our mission? So our mission is to safeguard the public health, safety, and general welfare through regulation of the design and construction of healthcare facilities to ensure they are capable of providing sustained services to the public. Okay, so that is our mission, such that hospitals that house patients who have less than the capacity of normally healthy patients to protect themselves, and that must be reasonably capable of providing services to the public after a disaster. Okay, so that is our mission, and this is our goal. Okay, and it's given in statute. Okay, this was what we call the first ever definition of functionality. You may have heard of the new new proposed legislation that we are trying to push forward through the legislation committee for SEAOSD on functional recovery. I said OSHPD was already a forerunner on that, and this is our mandate given right back in the 1983 Hospital Seismic Safety Act. So it also, the legislator in the hospital seismic safety code also gives OSHPD the authority to perform subsequent and post-earthquake studies. For subsequent to occurrence of any earthquake, the office may make or cause to be made studies of healthcare facilities within the involved area. So if there's any earthquake that has happened, then if to a hospital building, then OSHPD staff is immediately deployed to those hospitals to assess the safety of those buildings for continued operation. So it's similar to your seismic assessment program. We do that for hospitals. So we red tag or yellow tag or green tag hospitals after an event. So this is the authority that gives us that permission to go ahead and do that. Also given in law is the research ability to reduce seismic risk. So it is further the intent of the legislator that the office, with the advice of the Hospital Building Safety Board, may conduct or enter into contracts for research regarding the reduction or elimination of seismic or other safety hazards in hospital buildings, or research regarding hospital building standards. So we also have a requirement in law that we can do research to reduce seismic safety, right? So those are the requirements for legislator, giving us the authority to do what we are doing regarding seismic instrumentation. So how well did the Act of 1983 perform? Well, the test came with the 1994 Northridge earthquake. Everybody knows that. I happened to be in Southern California at the time, and it was scary at the time. So everybody knows that. And a lot of code changes occurred because of the damages and failures. But the Northridge earthquake. So how did hospitals buildings perform, right? So we have the 1983 Hospital Seismic Safety Act, and based on that, and all new hospital buildings were now under OSHPD. So how did those particular buildings perform? And here's the report card. So at 23 hospital sites, they investigated and they looked at it to see how did our buildings perform in terms of seismic response to the earthquake. So there were like the pre-act buildings that were pre-act is buildings that were built before 1973, and post-act are buildings built after 1973. So this is the 1994 earthquake. So he said, how did the building perform in terms of the structure, and how did the non-structural components perform? So there were 12 pre-act buildings that were red tagged. There were 0 post-act buildings. So that looks like, hey, that's pretty good. Yellow tag, there were 17 pre-act buildings, but there was only 1 building that was post-act that was yellow tagged. So yellow tag means only a small portion of the building could not be used subsequent to an earthquake. And then 30 buildings post-act were all green tagged. So these are for the 23 hospital sites that were looked at that time. But the non-structural damage, even that, in that case, even the new post-act buildings also, for the most part, even for non-structural, did pretty good. There was minor damage was high, but major damage was not as high. But it was not too bad, but it showed that whatever they were doing in terms of transferring the authority from locals to OSHPD itself, and looking at hospitals differently such that they can continue to provide services to the public after an event was kind of working. So how do we evaluate building performance to reduce seismic risk? So there are different ways you can do that. You can have a shake table testing. Your building that's an e-defense building. I think that's in Japan. And you put a building on a shake table. I was in Buffalo. I studied there for a while. We had buildings put on shake tables there, and you shake it, and then you see, and then you can retrofit it and shake it again. And so a lot of studies can be done, but that's kind of expensive, right? So and you cannot get the size and everything of a real building put on a shake table test. So it has some limitations as well. The other way you can check building performance is through analysis and mathematical modeling, okay? And then real-world laboratories, right? So real-world laboratory is basically instrumentation of buildings, and then you wait for the earthquake, and then you see, hey, how did that building perform based on my analysis? And then all the researchers will go and try to figure out what was the damage and can they predict the response and everything else. So the real world laboratory is where we are today. So recordings from instrumentation are critical to understanding building performance leading to design of safer hospitals. So you can do all the lab work or the analysis, but you actually, the proof of your efforts is how does it actually perform in reality, right? So the building that you're seeing is the new Stanford Hospital. I mean, it's a seismically isolated building. It has a number of sensors to capture the performance, the dynamic characteristics of the building. Okay, so how you locate the sensors, then we work with, OSHPD will work with Seismic, because as I said, the instrumentation program was created, Seismic was created to make sure they maintain these instruments. And then also we need to provide funding for these particular hospital buildings because they are not part of their mandate. They are still supposed to be in charge of it, but the funding source is different, and I'm going to talk about that a little bit. So here's where it comes in handy in terms of why we are instrumenting certain types of hospital buildings, because we want to learn more, we want to reduce seismic risk, we want to understand the performance of the buildings, and you can do as much analysis as you want, but till you actually do a full test, you really don't know how it is going to perform, and that's one method to do it. Unfortunately, the time frame in which the earthquakes occur, it makes it a little bit of a challenge, and people think, oh, you know, seismic instrumentation is not that important, but I kind of beg to differ, you know, on that. But we, as a matter of fact, most of the time we find that the number of instruments that we actually put in a building, you know, is not cannot adequately capture the full response of the building, but with the lower cost of instrumentations and stuff, you know, we may be able to put more sensors in different locations to really capture the buildings. And the goal is to also make sure that more buildings, hospital buildings and other buildings also get instrumented over a period of time. And through these efforts, it will help hospital safeguard medical buildings from future earthquake loss. So understanding and reducing the seismic risk, because we understand better how these buildings perform, will help us then help to design buildings better for functionality post-earthquake events. So there are two types of buildings that are instrumented with funding from OSHPD, right? I mean, so even though we may not be paying for it, I mean, there are two types of buildings under our purview. These are owner-paid instrumentation, and the other is OSHPD-paid instrumentation. So regarding owner-paid instrumentation is that when the building code dictates for your type of building, you will need to put seismic instrumentation, and those requirements are given in Appendix L of the California Building Code. And then also, if you have alternate methods of compliance for a seismic force resisting system, and also if you have seismic insulation or damping systems, then you would also need to have instrumentation for that particular building, because these are new technologies and we would like to know more. And it is also to help the future. I mean, are these buildings going to perform when you have seismic isolation and damping? Absolutely. The question is, how well do they perform relative to other buildings? And is that going to be now a way to have more buildings isolated or with dampers or things like that? But the proof will be, you know, how they've actually performed. But, you know, so those are the requirements for owner-paid instrumentation. And then OSHPD paid instrumentation is where OSHPD will, through the Hospital Building Safety Board, will figure out from a list based on geographical regions and the number of hospital buildings that are instrumented in a particular area and the building type, which is the next building that OSHPD will fund to have CSMIP go ahead and instrument those buildings. Okay, so that is those are the OSHPD paid instrumentation, and then the maintenance also. OSHPD was paying all this time, but now we are splitting the maintenance between where an owner has to instrument his building, because it required for the building code, we said, so if something happens to your instruments, then Mr. Owner, you will be paying for that maintenance. However, if it is an OSHPD paid instrument and something happens, then OSHPD pays. And so we have a contract, ongoing contract, which is renewed every 3 years with CSMIP, such that we can maintain this program. What are the references for requirements for seismic instrumentation given in the California Building Code? So there's a CBC section 104.11.4. It says buildings which receive an approval for an alternative system for the lateral force resisting system, section 1617A.1.39, buildings with seismic isolation and damping systems, CB section 603A. Now, for some of you who don't know what that CEBC section 306A is, this is last year, I mean, in the 2019 California Building Code, OSHPD decided to put its existing buildings under the Part 10 of the California Building Code. So then we adopted the California existing building code in the 2019 code cycle. So we created the A chapter. So you'll see chapter 3A. So it's section 306A. So in that, in that section, owners of existing structures that are selected by the enforcement agency for installation of earthquake recording instruments, so those buildings will have to be instrumented. Those are the OSHPD paid buildings. And then also Appendix L, the requirements are 6 stories in height and floor area greater than 60,000 square feet, or if it exceeds 10 stories in height, regardless of floor area. So those buildings also have to be instrumented. So how many instruments do you need, right? So that's always a challenge, right? So some say, oh, you need to only have 3 levels of instrumentation and triaxial instrumentation at each location, and you're good, right? But what Appendix L says that you actually need sufficient number of instruments to characterize a response. And as I mentioned earlier, every time there's an earthquake and we look at, oh, can I get drift? Can I get this? Can I get that? Oh, we cannot do it. And then we have to use approximate methods to come up with the missing data, right? So it's always a challenge from that, trying to get all the data out of those seismic instrumentation. So we want to make sure that anytime we recommend new hospital buildings, we are looking at it in terms of the flow accelerations at the roof, somewhere in the mid-height and at the bottom, or any levels of irregularity, etc. Then we have instruments there. And now we are also looking at how we can get interstory drift at floors that we expect, high drift. So we also work with the structural engineer to make sure that the right amount of instrumentation is done, because the owner definitely doesn't want to pay. He wants to pay for minimum number of instruments, and the more number of instruments that you add adds to cost, and also the recorder that they have, it's limited on number of channels, right? So if you have 24 channel recorder, then you can have 24 sensors put, and so those are all limiting factors in how we decide to strategically place instruments in the building to sufficiently characterize the building response should we get an earthquake. So here are the requirements I already talked about earlier for when the lateral seismic resisting system in hospitals is instrumented by owner, is when you have structures with passive energy dissipation systems, seismic isolation, other structures of conventional lateral force resisting systems with alternate methods of compliance, and then structures not listed in ASCE 7 table 12.2-1. So when there is buildings that are paid for by OSHPD funding to reduce seismic risk, okay, so what is the criteria that we use for that? So the criteria that we use is proximity to fault capable of generating earthquakes greater than magnitude 6.5. And sites with high probability of seismic events. I mean, so you don't want to you instrument buildings in low seismic areas because the chance of getting an earthquake there is low. So we want to make sure we maximize the put instruments in locations where there's a good probability that an earthquake can harm, because it is used for two purposes. One is to know the individual performance of that building, but also gives you a general sense of the seismicity in that area, right? So then the other thing is non-standard structural systems adjacent to buildings with pounding probabilities, buildings with irregularities, so you have buildings with torsional irregularity, soft story, weak story. So we make sure that when we look at these particular buildings, that these particular buildings probably are not going to collapse during an earthquake. So you want to also, but we think it's good enough and it's going to probably survive, but it will give us valuable data post-earthquake. So the idea of the instrumenting is, so post-earthquake, we can learn how those buildings perform, and researchers use that information to do a lot of studies to then improve the building codes and reduce seismic risk. So those are some of the criteria that OSHPD uses when they decide to fund hospital buildings. So on this figure on the right, which is in the green, you see the black dots there. Those are all our instrumented hospital buildings. We have 88 hospital buildings that are currently instrumented and maintained by OSHPD through the California Strong Motion Instrumentation Program. And you can see those plotted on Google Earth here. So which are the buildings, as you can see, wherever there's strong motion coming, then we have decided that, okay, that building, it's either through OSHPD funded instrumentation or through owner paid instrumentation. We will get some of those buildings instrumented, and also based on the geographic regions where they are, so we get spatial distribution adequate to capture the response should it occur at that location. So here the number of sensors also depends on the type of building. Like if you're having a seismic isolated building, you put more number of sensors. Like this one, Stanford had like 36 accelerometers. That's pretty high. One higher than that is Loma Linda University that's just being constructed. Like they have about 44 sensors. So that building is that was a building that was supposed to be on vertical isolation, but the vertical isolation part of that did not materialize. But however, it's a base isolated building with dampers at the base location, so that you can reduce the amount of acceleration at the base. And then it's a 16-story building and a 10-story building side by side. So it's a very complicated building, and so in order to adequately capture that dynamic response of the building, then we needed a lot more number of sensors. Okay, but so depending on the building, the number of sensors could vary. We also use these seismic instrumentation data for a particular site for EOC applications, emergency operation center applications. Nowadays, with the new instruments that you have, we can get near real-time communication from the site location submitted to Sacramento, and then that gets submitted to our emergency operations center, and we use that as a means in which we can deploy people to the site to check on their particular building, and also based on that we look at the seismicity in the area to get an idea which particular buildings would need to be looked at in terms of safety for the hospitals to then red tag or green tag those buildings so they can continue to provide service post-earthquake events. What are some of the applications of seismic instrumentation? So to evaluate response of buildings to strong ground shaking, it acts as a surrogate for shake table testing, calibration of computer models, validates dynamic characteristics of the building, estimation of non-structural damage, building resilience, And then last but not least is recommended changes to the building codes for improved performance. So every year, CSMIP gives out contracts to researchers to then do research to then try to find out with existing data and existing ground motion studies what they can learn to then improve the building codes so that it can reduce seismic risk. So here is one such example. So this is, people may have seen this particular building many times. This is the famous Holiday Inn 7-story Van Nuys building. So a lot of researchers have done research on this and they've tried to simulate it. Now, the interesting part about this building and why this one is important is because this had a lot of damage and the behavior of the building was nonlinear. This is some of the studies that I did to show comparisons of the displacements at the different flow levels and with the recorded one. And as you can see, this was using the program that I developed, IDOC 3D, to see how we can capture that. But you know, it is used for that. And then other researchers, like this is one by Sashi Konath, is working on a current contract with CSMIP to then look at a steel building and then use this data for then recommendations to the building code. So those are for the building itself, and then you also have applications for non-structural components. Now, the Sylma 6-story county hospital, this is another hospital that was heavily instrumented prior to the Northridge earthquake, and there are many flows that were instrumented also. As you can see here, you have the ground flow, third floor, fourth floor, so you can get interstory drift and also the roof plan. So then this location of this particular building also showed the amount of acceleration, flow accelerations that you can get. So from there, you can get once you get the acceleration at each flow, then you can do a response spectrum. You can get the flow spectrum. From there, you can say, okay, if this is my response at a particular flow, what is my expected performance of my non-structural components in terms of accelerations? Because the stiffer you make your building, the more forces you can get. As you can see, the spectral acceleration for different channels at the different flow levels, you know, you can get pretty high values like 6G and things like that, you know. So it's pretty high. And these data have been used by researchers through the also partially funded through the SEASMIP instrumentation program to then look at your F sub P equation in chapter 13 of ASCE 7 and then say, okay, how can we use this data that we have from strong instrumentation, strong ground motion instrumentation to improve model building codes? And so then they come up with a new equation here, which is probably going to be coming in the next version of ASCE 722. So there's a lot of applications for that. And then in addition to instrumenting buildings, for general science, there's also instrumentation buildings to know the health of your particular building itself. And if you want to look at one particular building, then structural health monitoring of the building is important because post-earthquake, there's what's called aftershocks, right? So how well is your building going to perform and how depends on that, what is the damage? And then also the information that you can gain from those seismic instruments, you know, can be used for future research and development for to reduce your seismic risk. So what are some of the reasons for monitoring? So that's one of the instrumentation, and the other one is structural health monitoring. So if you have an instrumented building, why do we need to monitor that also? And here are some of the reasons. So that medical facilities need to be operational after an earthquake. It's for early assessment of integrity of the hospital, for aftershocks, and resiliency and sustainability. So if you know your building characteristics, you know what happened, then you can know the output, then you can also use that data to say, if I design a building this way, but another building similar to that, this is my expected performance. You will not know the real performance, you will know the expected performance of that. So with that, are there any questions? Sorry, I took a little bit longer, but
thank you, Roy. I'm not seeing any questions yet in the chat. If anybody would like to speak up and ask a few, well, I see Victor's typing now, so I'll let him finish typing. Or if he just wants to unmute himself, he can ask his question himself instead of typing.
Quick question on the instrumentation. So you guys also do vertical acceleration instrumentation, especially on the isolated buildings?
Yeah, we do have some vertical acceleration sensors in Loma Linda only. But it was also to measure if it was supposed to be vertically isolated, but that didn't materialize. But we do have sensors to check vertical acceleration.
And that one is isolated. Oh, it has a spring, vertical springs, right?
It does not have. That did not materialize.
Oh,
that was a plan.
Yeah,
it did not materialize. But that would have been interesting because but the cost was too high.
Right. Okay. Yeah, I was thinking on the Stanford one because that one has the base isolation, and it has only the horizontal ones.
Right.
Victor had a quick question, then we'll move on to
yes. Thank you, Roy. Roughly, how much is the average cost of installing one instrument? And secondly, like, what are we talking about in terms of maintenance costs per year?
Yeah, I typically don't get into that cost, but are you talking about one instrument or instrument one building? Yeah.
Well, maybe one instrument to begin with, because I have no idea how many would be an adequate number of instruments to consider whole building instrumented, but at least to give us an idea, say one floor of a building.
I could be 100% wrong. Maybe somebody like from SenseQuick may be able to give a better answer, but I'm just guessing like $1,000 per instrument sensor. But then in addition to that, you also need a recorder, which could cost like $20,000-$30,000.
Wow.
To do that. So and by the time you get enough sensors in your building, you're talking close to $100,000 for seismic instrumentation.
Wow. And then subsequent maintenance per year?
Maintenance, it depends. If you put new equipment, it may be, it depends what Seismic charges. They charge us a certain amount per building, per year. They charge us like $500 for monitoring only, and then maintenance is on top of that. Basically, that's one of our mandates to do the research. Therefore, we fund that because we believe that seismic instrumentation is important for knowing how these buildings perform in the future. It's more for research work. Yeah.
Okay. Thank you.
All right. Thank you. Thank you, Roy, for your presentation. With that, I will hand the reins over to Michael Hill, Senior Structural Engineer with the City of San Diego, to present on their instrumentation program.
Hello, everybody, and good afternoon. Let me get my screen up here. I hope everybody can see that. Yes,
we can. Thank you very much.
Okay. As I was introduced, I'm a senior structural engineer with the Division of Building and Construction Safety here in San Diego. Ali Fatah developed this PowerPoint to basically go over the impact of this instrumentation in this, how it impacts our community, the city of San Diego, and our development. And it's a much smaller region than what Roy has to deal with, so this will be a much shorter conversation. Ollie can't be here today because he's out at the, I think he's in Chicago for the ICC conferences out there, IBC conferences. Anyways, moving on, we'll be talking about the two code-based triggers that require the installation of seismic instrumentation here in San Diego. The applicability based on building type, number of stories, and project location. The other things we're going to consider is why we'd like to see the earthquake instrumentation. We'll talk about the installation inspections and functional testing, and about the post-occupancy system maintenance and repair. The authorizing documents for this requirement come in two different places. One is Appendix L in the CBC, which we adopted since the 2016 Building Code, without any changes, except we don't include the OSHPD amendments. The other one is for tall buildings. These are alternate means of compliance to the building code, as Roy was talking about. Most of that comes through our structures that are higher than the structural height that is allowed by the building code. And we use, or we follow the LA Tall Building Design Guides or the TBI design guides. In Chapter 5 in the LA Tall Building, Appendix A in the Pier Tall Building Initiatives. And we follow what they require for these alternate methods. I don't think we have any structurally isolated systems here, but that may be required when we go down that route. Talking about the reasons we like to see these instruments is, well, for one, we collect money to put these into buildings, and these are funded through our permit process. These help inform the local designers about the ground motions here. They should help in the design of tall buildings considerably. There's not a lot of information being collected. I know the Rose fault, I believe, is the most prominent fault in the area, and they should be able to get some better readings and do a better design of the structures, especially for the performance-based design structures that we have going on here. And we have quite a few going on right now. We have half a dozen in the works. Let's see. Starting with Appendix L, that requires that the buildings, when the acceleration is greater than when the S1 acceleration is greater than 0.4, and the structure either exceeds 6 stories in height and an aggregate floor area of 60,000 square feet, or the structure is over 10 stories high, then Chapter L requires this instrumentation. Now, in San Diego, what that means, if you're familiar with San Diego, 0.4 acceleration is basically west of the 805 all the way up to Del Mar. And east of the 805 is less than that, so those are not going to be needing this instrumentation. This includes everything downtown, in La Jolla and Claremont, and all the way up the coast to Del Mar. And anything that is over 10 stories in height is also going to require that within that 0.4 area. In the 29 CBC Appendix L, I skipped a page here. Appendix L structures need to be equipped with 3 or more approved accelerographs, and the accelerographs need to be interconnected for a common start and common timing. And generally, what I've seen is 3 being used in most of the installations that aren't the performance-based design. Usually, communication wiring is installed to connect the top and bottom device to the mid system and storage transmitting system. There are no requirements for remote communication, so remote monitoring will have, there's no remote monitoring, so the data is all collected from the building. and there are no requirements for and these are not monitored by CSMIP. The CSMIP people are definitely involved with the tall buildings that we have here. These systems are much more elaborate and can include up to 30 or more instruments. The instruments are distributed over the building's height and measure in all three directions, and they're connected directly to CSMIP. The instrumentation plans for these buildings are reviewed by CSMIP and approved by CSMIP. Generally, they approve anything that is that meets the requirements of CSMIP will be monitored by them and approved by them, and also I believe they are maintained by CSMIP. For the tall buildings that we have, like I said, there are 30 or more that are needed, required by LA Tall Building. They're installed all along the building height and the basement. Remote communications go directly to CSMIP. They're not, and they're not, the instruments are not monitored, but the remote communication goes to CSMIP to be recorded. These are for systems designed either by TBI or LA Tall Building. And again, these are the performance-based design buildings that we've been doing around here. For Appendix L, installation and commissioning procedures, the equipment is installed by the equipment manufacturers and is inspected by the manufacturers as part of the statement of special inspections. They get written certification to the building inspector that these satisfy all of their requirements. For the tall buildings, those installations are inspected by CSMIP, and they do the commissioning of the equipment as well. CSMIP issues a letter to the building inspector saying that these meet their requirements and they're good to go. For maintenance and repair, Appendix L for the non-performance-based buildings, the maintenance is done by the property owner. The manufacturer monitors the equipment and performs regular inspections. For the tall buildings, these are also maintained by the property owner, but CSMIP notifies the owner of the trouble to maintain and replace the equipment, so they keep an eye on it. And as far as the equipment that is qualified for the CSMIP program, they will generally take anything that meets the requirements for the California Geological Survey systems. They will take the same equipment. And actually, that's the only equipment they'll take. What else here? We do have a technical bulletin on our website that tells the contractors and owners what the requirements are for the instrumentation. It's Technical Bulletin 16-1, and it addresses, that also addresses how long the equipment can be out of service and what needs to happen to get it back into service. And this was developed based on the LADBS information bulletin on the subject. So we'd like to keep these going as long as possible and as maintenance free as possible. And like I said, this is going to be much shorter than Roy's. So if we have any questions, we can take them now.
Thank you very much, Michael. I'm not seeing any questions in the chat window yet. So while people are hopefully preparing a few questions, I've got one for you. How many of the, I guess, non-performance-based design buildings that are under construction right now in San Diego have actually been or have been built, have been instrumented?
This hasn't happened. As far as I know, there are a handful only that this has affected. And that would be the most. A lot of the buildings downtown, any of the new buildings, and none I can think of off the top of my head, but I know of only, I have heard of only three or four, less than a handful that have this requirement, have satisfied this requirement, have needed to satisfy this requirement.
Okay. And from a city's perspective, when I guess you're putting together a set of standard structural construction drawings, we would basically just need to list some either some notes or something in the special inspection table regarding the seismic instrumentation program.
Yes, those will be listed in the statement of special inspections, and I believe there is an agreement that the owner has to have with the city about the maintenance of that.
Okay. We got a question from Victor Garcia. He's asking, how tough are these instruments and what is their record throughout a large event in terms of being able to survive it?
Victor, I do not know. I have, here in San Diego, we have not had that large of an earthquake since these have been put in, for one. None that I know of. I do know of one building where the instruments stopped working, and I don't know the outcome of that. I know they were talking about just abandoning them. That wasn't due to any shaking. It was, I think that was just a maintenance problem that they were having with them. But I don't think we've had anything fail here from the earthquakes that we've had here since these have been started, since the program started.
Victor's tapping up. Oh, he's saying thank you. Well, do we have any other additional questions from our attendees? Well, thank you both to Roy and to Michael for presenting, and especially for Sensiquake for sponsoring our event today. We'll leave the chat window open for a few more minutes if people think of a couple of other questions. Otherwise, this concludes our presentation today. So thank you all for attending. We hope to see you at our May meeting where we do our part 2 and our deep dive into the SoFi Stadium up in Los Angeles. Thank you very much.
Thank you. Thanks, everyone.
And Heather, if you're still on, you can stop recording.